Right, welcome back. Today is the 25th of February, 2022. And for today's lecture, I will actually re-record this part 03C and put it up into the YouTube. So this part of the lecture notes, 03C, is not in YouTube. And we're going to redo this. Now, before that, I would suggest you look at the lecture notes. And I have also prepared one slide in which I find that Van Veen's lecture have two lectures on DFT and convolution of using DFT, which we are going to do today. I would also put this up and suggest you look at these slides and these videos in the YouTube as well. All right, let's begin. So the first question, of course, is that if we have discrete time Fourier series, discrete time Fourier transform, why do we need another one? Okay, so I will answer this question first and let's proceed. This is the diagram that you should memorize and you should copy into your cheat sheet. We are mainly focusing on discrete time Fourier series, Fourier transform, and DFT. To recap, discrete time Fourier series is for periodic discrete time signal. So this guy is a 5-point and it repeats. Discrete time Fourier transform is for aperiodic signal of infinite length. In this case, we have zeros and then some values and then lots of zeros. But actually, for discrete time Fourier transform, it can analyze an infinite sequence. So these guys do not need to be zero. Okay. But in this particular examples, we are going to show you that at least for these 5 points, these 5 points are exactly the same. So there's a deep relationship between discrete time Fourier series and Fourier transform when the sequences are the same. So if we have periodic signal and we have non-periodic signal, there's nothing else. Well, actually there is. You have said that in a particular sequence, we are actually looking at the sequence. And if we look at only 5 points and not look at the thing outside, then isn't these 5 points the same as these 5 points and these 5 points? And could we not perform a Fourier analysis on it? And this is exactly what DFT is doing. This DFT is looking at 5 points, for example, a 5-point DFT, and ignoring everything else that is outside. This outside, guys, does not need to be periodic or aperiodic, and it does not need to be zero. It can be any points. So these 3 pictures, therefore, are sort of different. Now let's look at the equation for DFT carefully. DFT says that if I have an n-point DFT, I only need to look at n equals 0 to n minus 1. So 5 point means 0 to 4 point. You look at this equation. I will take the input signal xn from 0 to the 4 point and multiply with this complex exponential and sum it up. This equation is the same as this equation, n equals 0 to n minus 1, the input signal and this. So in fact, the DFT and the DTFS is exactly the same except with this 1 over n. 1 over n will normalize this value. Okay, so therefore DFT and DTFS are identical except the difference of 1 over n. Now, let's go back and see what is DTFS. If we can generate the coefficient ck from k equals to 0 to n minus 1, then we can take this ck and use it to regenerate xn. Now, if you remember, if there's a 1 over n here, and this guy has no 1 over n, therefore the 1 over n appears here. Okay, so there's actually no difference whatsoever, except this 1 over n moving around these 2 places. But please remember, what is the assumption? DTFS is analyzing a periodic signal. DFT is also analyzing this 5 point. If these 2 equations are the same, from the DFT's eyes, actually this input signal is being repeated. And that will cause some problem later on. All right, so let's proceed. So in fact, from the DFT world, let's take this input signal and let's take only this white part. And this white part, let's for example, we have what 0 to 14. So we have about 15-point DFT. Now, when we perform DFT, we are actually performing this. We are thinking that the input signal is a periodic signal. Okay, that's the clever idea, but also it causes a lot of problem. What is outside here, we do not know. But in the DFT world, when you perform DFT and inverse DFT, you technically can generate this signal here and this signal here, but you'll be totally wrong. Okay. All right. So how can we interpret DFT and DTFS? So DFT and DTFS is nothing but a scaled version of each other. That's the first point. You can read the slides. Second point is that we can interpret DFT as a sampling of DT, what do you call it, DTFT. The DFT is nothing but sampling the points at different frequency of the DTFT representation. So the DFT of XK at the frequency or at the kth harmonic is nothing but the value of DTFT at the K times the omega naught. The omega naught is 2 pi over n. So at this frequency. All right. So these are the two interesting interpretation of how is DFT related to DTFT as well as DTFS. But actually, I mean, if you go and only understood this picture and this equation, you'll realize that this guy and this guy are the same with except 1 over n. And what about this guy? Omega is 0 to 2 pi. But here, omega is only 2 pi over n times different values of k. So that is why it's called a sampling version. Omega is continuous here. Here is not continuous. It's at different frequencies of k. So I have just very quickly in the last few slides talk about part 1. So I will pause now. Right. In the next part, I'm talking about circular shift and circular convolution. I will also suggest you listen to Van Veen in this link. So if you just search for Van Veen convolution using the discrete Fourier transform, you will be able to see also this video. Now, let's proceed. Right, the word circular shift and convolution. Circular shifting means basically as we are rotating a buffer, for example, if we have a buffer that is 4 elements long, 1, 2, 3, 4, and then we are delaying it, then you'll be 1, 2, 3, and then this guy has gone out and come in is 0. So for example, as we are pushing the buffer 1, 2, 3, 4 on the right hand side, then the new value 0 comes in, and this is very similar to the problem of x of n and x of n minus 1. So x of n minus 1 is a delayed version of x of n. 0 comes in.
Prof, if you shift one more time,
So if you shift one more time, then you have 0, 0, 1, 2.
Oh.
So that is the linear shift. Okay, so this is x minus 2. I'm talking about if we can only observe. Yeah, I'm talking about only if we can observe only these 4 points. Okay, we're not interested in values outside these 4 points. That's what I'm saying. Please don't be mistaken that I'm drawing xn minus 1. I'm just I shouldn't say that. I should say delay, or let's say shifted by 1 element. Okay, so I should be saying that. Now, a circular shift basically have this operation. What I will now show you the figure. So this is the let's say the n element of my x of n. Now, if I generate a periodic extension of this, then it is nothing but taking this and repeating this. So that is what DFT is doing. If we are only analyzing n point and whatever value is outside, we don't care. When we perform DFT and inverse DFT, then outside this sequence of 0 to n minus 1, it is the same repeated sequence. That is the problem. And the problem comes when you see I'm going to advance this by 2 samples. So I'm going to shift this onto the left. So I'm advanced by 2 samples. So when I advance by 2 samples, what happened? In the original, if I have this guy, and if I advance by 2 samples, then I would be having 1, 2, 1, 2, 3. What will happen? I will have this, 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 and then 2 zeros. So this thing actually is gone on the left. And if I'm only observing the endpoint, I would only observe this thing, and 0 is shifted in. That's the linear shift. In a circular shift, what happened is this. Okay, is that because this sequence is being repeated, therefore the circular shift is not shifting 0 into the what you are seeing. It is shifting the head into the back. That's why it's called circular. All right. So that is the problem. Now, circular shift is not something we want. It is an artifact of DFT. Okay, so that's the problem. So first you understand what circular shift, and now we understand what circular convolution. So this is convolution operation. Actually, it is like this for convolution and like this for circular convolution. What's the difference? Circular convolution. What's the difference is that now this delay is not a not natural delay anymore. It is the modulo n circular shift. It means that things from the head will shift to the tail, or things from the tail will shift to the head. Now, what will happen is this. All right, so you go and read. Let us now see this problem. All right. I have input that is 1 and 2 being sent into a filter that is A, B, and C. And of course, we want to perform a convolution to get Y. And first we write the convolution equation, X is convolved with H, and we write this convolution equation, and we know how to solve this. In fact, this is quite trivial because we only have 2 points. So I have x0 multiplied by the impulse. The delayed version of x1 multiplied by the delayed version of the impulse. That's it. So from here to here, you can see what's happening. Now, where's the problem? Well, if it is a linear system, linear convolution, there's no problem because, well, this is, what do you call it? Isn't this, this is, oops, this is 1, which is equals to x of 0 multiplied by h of n. So we got ABC exactly at this point, not a problem. The second guy, which is 2, the 2 value, but he's delayed by, he's now at n equals to 1. So he will introduce a delay to a scaled version of the impulse. The impulse is ABC, the scale is 2, so it's 2 ABC, and the position is delayed by 1 sample. All right, so we know that, hey, we can sum this because this is a linear system. So we just sum this and we get the output. So this is a linear convolution. But what happened when this guy, this delay version of Hn is not the linear delay, but the circular shift, right? So because I have 3 samples, so what happened? Then you'll realize that the Hn is now being repeated. 0, 1, 2, then repeating. 3, 4, 5 is repeating 0, 1, 2. So when we are performing a delay of this guy, the green thing comes in. Can you see? The green line comes into 0, 1, 2. Now, what happened is that, therefore, when we are doing scaling, it will be 2 times the green guy, 2 times the red guy, 2 times the red guy. And this is what happens in circular convolution, which is, of course, not the same as the left-hand side. And therefore, the result is wrong. So guys, if you now understand the difference between the linear and the circular convolution, how would you solve the problem? So you realize that why the circular convolution arises. The circular convolution arises because I'm going to use frequency domain multiplication here to realize convolution. DFT multiplication is circular convolution. That is why circular convolution arises. So how are we going to solve this? Because this is not what we want, right? So the trick is, how are we going to implement? So the trick is, so this is the trick. All right, I'm going to show you the answer first. We are going to do 0 padding. Now, remember we have 1, 2, 3, right? And I pad extra 0. And then I repeat 1, 2, 3. So I make my HN, although it was 3 steps long, I just pad it with 0. Since I'm padding with 0, technically nothing has changed, right? To the system. Please be convinced by yourself that if I have HN is 1, 2, 3, followed by all the zeros, then there is actually no difference when I say I'm going to use DFT with endpoint equals to 4. When I use endpoint equals to 4, is 1, 2, 3, 0, then repeat 1, 2, 3, 0, and repeat. So HN now is a periodic 4 sample, as opposed to the previous one. HN was a periodic version of only 3 sample. Let's see what happened. Now, okay, so if he has 4 samples on the right-hand side, what is this? Even though it's circular convolution, it means that I have to repeat those guys on the left and those guys on the right. What happened is that little extra 0 in the tail is being pushed in. This 0 belongs to the previous set, and 0 is being pushed in. Isn't this what we want? If you remember, when we are doing HN minus 1, we're pushing 0 onto the left-hand side. So by this clever idea of 0 padding, we now can realize linear shifting on circular shifting problem. Okay, that's the trick. Okay, so you can read what we have just done here in these last few slides. All I'm saying is that all we need to do is to pad zeros before we repeat. And if we pad enough zeros, the shifting would not cause a problem. Okay, so now let's try. We are now using circular convolution with 4 samples. So you realize that the first guy will generate 1, 2, 3, 0. The second guy will also generate 1, 2, 3, but since it's delayed by 1 sample, the 0, which is padded on the left, gets shifted in. But since it's 0 shifting in, it doesn't affect the answer, and therefore we get this correct answer as in linear convolution. Okay, that's the trick. I'll pause now, the questions. So I'll repeat the explanation slowly. So I have an impulse response 1, 2, 3. Can we also say that the impulse response can be 1, 2, 3 followed by many zeros? This is equivalent, right? Whether I say the impulse response is 1, 2, 3 followed by 0 is all like this. I should write like this. Now, therefore, when I perform linear convolution, I take the first input and convolve with this guy. I take the second input and convolve with this guy. I get these 2 pictures. Is that correct, Hauke?
Yes, yes, Prof.
So I should be writing all these now. Agree? All zeros. But what about this guy? What happened here? On this point, isn't 0 shifting inside? Because it's nothing but this picture shifted right. 0 is shifting in. Agree?
Yep.
All right. Then the answer is correct. Okay, so this is linear convolution. Now, in circular convolution, remember my 3 sample, if I'm taking n equals to 3, it means that my input sequence is 3 samples. And I'm actually repeating him 3 samples with nothing in between. That means that it'll be 3 samples. The next 3 samples are the repeating version of this guy. So clear?
Yep.
All right, how did this happen? It is because I'm going to perform DFT on 3 points. And when 3 points, and when I inverse DFT, this will happen. This is a phenomena of DFT. Now, when I shift by 1 sample, because when I shift 1 sample to delay, what will happen? This point, can you see now? This point, what will happen to this point?
It will disrupt the
He will be
signal.
shifted in.
Yep.
And therefore, this Hn minus 1 is not the same as what? It's not the same as this guy anymore, right? Can you see? Agree? Because, yeah, right? He is being shifted in, right? Okay, so therefore, the answer would be wrong. So what should I do? I want to shift a 0 inside, right? What do I do? I cleverly, what? Instead of 3-point FFT or DFT, I add an extra 0 here. And then I repeat him. Can? So I'm doing 0 padding. I'm extending my Hn by 1 extra point. So now I have 4-point DFT. Therefore, now the sequence looks like this in the DFT world. What about delay by 1 sample? Then what happened? This guy push in, right? Can you see? From here. So isn't this exactly what we want? The delayed version of Hn? 1, 2, 3, right? Therefore, when we do this, then the answer is exactly what we want. Now, many students will now ask, why don't we pad 2 points? So n equals to 5. Then what will happen? We pad 2 points. So now our DFT is looking at a 5-point problem. 5-point problem means I will have a repeating 5-point sequence. Okay, every guy is 5 points. It looks like 1, 2, 3, followed by 2, 0. So when I do a delay shift by 1, then what happens is that these values get shifted in, followed by this value. All right, let's try. So I can now do 5 points DFT. So when I shift, it's 0, 1, 2, 3. So this 0 was from the previous guy. I get the correct answer. What happened? I can shift again, and then I will get 0. Because what happened is that the next input comes in, it will generate output 0. So instead of generating a 4-point, which is 1, 3, 5, 3, for 5-point, I will generate 1, 3, 5, 3, followed by 0. Doesn't matter. Now, guess what happened if I generate the 6-point? What do you think this point would be? Okay, so in fact, you will repeat this sequence. All right, that's the interesting idea. That means what is outside this 5-point DFT actually is a repeat version of this guy, always the same. All right, I'll pause here. So now I would resume and talk about how to use DFT to perform linear convolution. So the clever idea, of course, is that we know that in time, it looks like this, and in frequency, it looks like this. That means we can convert Yn into DFT, or here, Fourier transform, into Y e j omega, H becomes this. So convolution in time becomes multiplication in frequency. But we have also realized that when we are performing DFT, then we have to do something. First is we have to choose the correct n. What is the correct n that we have chosen? Well, so so this is the n that we have to choose. What is L and M? Well, let us say that the input we were talking about, our example was L equals to 2. We have two input, x0 and x1. And what is impulse? In our example, M equals to 3. So we show you that if we do 3-point DFT, it's not going to work. We have to do 4-point DFT. Okay, so the big N must be at least, big N must be greater or equals to 4. Where did this 4 comes out? It's actually L plus M minus 1. Okay, so I think, well, did I get it right? Yeah, there. L plus M minus 1. Can you see on the top? The length of the output sequence must be L plus M minus 1. Okay, so the big N, the number of points in DFT must be equal to L plus M minus 1. So with that knowledge, then what you do is that, so originally my X was 2 points, right? So my endpoint DFT was how many? Was 4 points. So I have to pad how many zero? I have to pad 2 zeros. So it must be 1, 2, 0, 0 for my X. What about my H? My H was equals to 1, 2, 3. So what do? I pad 1 extra 0 here to make it 4 points DFT. So I have 4 points of X, I have 4 points of H, and then what do? I can generate X and H, and then I can multiply them together. So I have Y. Once I have Y, to get Yn back, I perform inverse DFT. So this picture very, very quickly tell you how to use, what do you call that? DFT to perform linear convolution using DFT, circular convolution. The trick is always to zero pad such that we have no more issues about circular convolution. The values from the other sequence is being pushed into my n equals 0 to n minus 1. Okay, I'll pause now. L is the length of the input. My input X in my previous example was x0 equals to 1, x1 equals to 2, right? That's all. My length is 2. Agree?
Oh, okay, okay.
My H was 1, 2, 3, right? 0, 1, 2. My length is M is equals to 3. Agree? For my previous example.
Okay.
So I need capital N, to be N equals to L plus M minus 1. So I need how many? I need 5 minus 1. I need capital N equals to 4. Can you see now? Endpoint DFT. Now, what happened is that since your input is shorter, so your input was only 1 and 2, what do I have to do? I have to do 1, 2, 0, 0. Agree? This is called zero padding. Just now, my H was equals to 1, 2, 3, right? I have to do zero padding. So my new H is equals to 1, 2, 3, 0. Agree? I now have X and H to be the same length. I perform endpoint DFT on each of them. I get XK and HK. Because they are the same length, I can I can multiply each element by the other guy to get YK. So when we say YK equals to XK, HK, what do I mean? It means that you have X0, you have the big X0, you have the big H0 multiplied by itself. You have the big X1, H1 multiplied by itself until Xn minus 1, Hn minus 1 multiplied by itself. So you have a vector of n element for Y. So this Y, this is YK, can then be, this YK can then be using this endpoint DFT, inverse DFT to get yn. Is this clear?
Yes, thank you.
Thank you. Pause now. Now, in all the Fourier transform, after you learn what is the meaning of Fourier transform, we are always asking you the properties, all right? So the properties that we are interested in is only this, linearity. That means when the input is multiplied by a constant A1, then the output is, after this Fourier transform representation, is also multiplied by A1. Each of these, if we have x1 and we have x2, each of them can be analyzed independently. So that's what the linearity means. The other thing is time shifting. Notice that we have this bracket here. This is the circular shifting, okay? And we always have endpoint. So if we shift, then it will be the repeated sequence being shifted into the 0 to n-1 sample. All right, so we are interested in shifting as well as, I guess, we are only interested in primarily these three properties. We have shown you that circular convolution. So this is the circular convolution symbol. He tells you what n is because things are only valid between 0 to n-1. Then we are going to play with the multiplication in the frequency domain to get the circular convolution. All right, so these are the only three properties. The rest we'll ignore. Now, DFT can be represented as a DFT actually can be represented simply as a matrix multiplication. This is x of k. K equals to 0 to n-1. So this is the Fourier representation in the frequency domain. This is x of n. And you realize that this matrix, which is n by n, this is an n by n matrix, multiplied by n by 1 vector, will give you n by 1. This matrix is a DFT matrix. Now, look at this row multiplied by this column. Isn't this the same as summation of xn? N equals to 0 to n-1. So I am showing you this column, each of these elements. N equals to 0, n equals to 1, n equals to n-1. So I'm showing you this. What about this guy? You take this whole thing and multiply by this, so it's a row by a column vector multiplication. What is Wn? Well, isn't this E minus J 2 pi over n k little n? You realize that this guy, yeah, I'm going to change n. So n goes from 0, n equals to 0, n equals to 1, n minus 1. This is k. So what is Wn? Wn is this. What is Wkn? Is this. So you realize that very compactly, we can represent DFT as a matrix multiplied by a column vector. Okay, so this is this what this two slide is trying to tell you. All right. Now, in fact, if you understand it from a linear algebra, and you realize that this operation is transforming a vector from one basis to another basis, or this can be considered as a linear transformation. In fact, if you understand DFT from linear algebra, it is much, much easier. Okay, I'll pause now. Now, if we look at the W matrix, the DFT matrix, the first row, okay, if we plot the first row, what is the first row? The first row is k equals to 0, right, for the first row. So this is k. And n equals to 0, n equals to 1 until n minus 1. In this case, I'm plotting for big N equals to 8. Actually, you realize that I have just divided the unit circle into 8 different parts. And then I'm going to plot the value of the angle. I'm not interested in the magnitude. The magnitude is always 1. So the only thing that is changing is this little guy here for different N, for different K. And what is this part? Isn't it 1 angle theta? So this, I'm going to plot theta. And here, the first row, the phasor is always pointing here. If you work this out, when K equals to 0, then isn't it E minus J0? What is E minus J0? 1 angle 0. Isn't this 1 plus J0? This phasor is showing you 1 plus J0. So the first row is nothing but a constant 1 for all 8 points. Now, if you have figured this out, then now let's try K equals to 1. When K equals to 1, so this guy is 1, N equals to 0 to N minus 1. So what do you think this is? It's 2 pi divided by 8. I have just divided a circle into 8 different parts. N equals to 0 to N minus 1. I'm going to move my arrow. And each time I move my arrow for 1 step N, I'm going to move by 2 pi over N radian. So he's rotating clockwise. And after 8 times, or after N minus 1 time, he's going to reach the last point. At the nth time, where is he going to land? He's going to land exactly here again. So it will take N times before he repeats. So this is K equals to 1. What is the interpretation? I will move and rotate a phasor clockwise in N step. So the tabular matrix is a very beautiful interpretation. Each row represents the different harmonic. This is a 0 harmonic, means the, what do you call that? It's a constant. Here, K equals 1 means that I will rotate the complex phasor in, and I'll take N step to rotate it. K equals to 2, in N step, I will rotate twice. See? Rotate once. So here, N equals to 0. Here's N equals to 4. N equals to 0, 1, 2, 3. 4th time it repeats. 5, 6, 7, 8 times he repeats. So K equals to 3. He will rotate. He will generate 3 complete cycles in N steps, and so on and so forth. So if you interpret the DFT matrix as this, then it is very easy. Once you have understood this, then it is nothing but taking this guy and each of these row and multiplying by the different x, and I'm going to study what is the relationship of my x with respect to different phases rotating at different frequencies. And that's all. Okay, so when you understand DFT in this manner, then you can interpret what is x of k. It is nothing but measuring my x of n, multiplying with a vector of this W matrix at different k. Okay, I'll pause now. Right. So actually, if you play MATLAB, you play Python, SciPy, you don't have the word FT. You don't even have the word DTFT or DTFS. You don't even have the word DFT. You only have the word FFT. So the FT is Fourier transform. The F stands for fast. Fast Fourier transform is implementing DFT. That's all. Okay. So whenever people are saying FFT, they are actually talking about a fast version of DFT. Why? Because a DFT will take n squared computation, while FFT will only take n log n. And there is a very big advantage in taking n log n. All right. So the last one. We have discussed why zero padding already. One of the reasons is actually if I only have a sequence of 1 and 2, for example, if I have a sequence of 1, 2, maybe until 118, for example, if my X. Now, actually, 118 is it's not a very nice number. What are the nice number in math or in FFT is 0, 2, 4, 8, 16. What do you think these numbers are? These numbers are nothing but 2 to the power of n. Okay? So we like numbers that are 2 to the power of integer n. And then there are many reasons. One of them is that it will allow you to decompose the problem for FFT to be very fast. So later on, you realize that we will convert this number, I guess, up to, we'll zero pad this until 128 samples. Any samples longer, let's say 130 sample, we'll pad it until 256. So things like that. Okay. Now we zero pad to add zeros, so we perform faster version of FFT. The other one is we increase the frequency resolution in the horizontal axis. Remember, we are dividing the horizontal axis of Fourier transform by n. So if we divide only by 4, actually we only can see, for example, n equals to 4, then we can only see 2 pi over 0. 2 pi over, oh, sorry, what am I doing? We can only see, if n equals to 4, then we can only see 0, 0.5 pi, 1 pi, and 1.5 pi, because this is 2 pi times 0, this is 2 pi over 4 times 1, this is 2 pi over 4 times 2, this is 2 pi over 4 times 3. So that is how you get the horizontal axis. You first divide 2 pi by n, and then for each of these points, you are setting k equals to 0, 1, 2, 3, and then you repeat. Now, if you have a very big n, then you are actually dividing the horizontal axis by a very, what do you call that? You're getting a very fine resolution along the horizontal axis. So you can increase the frequency resolution. Okay. All right. Then the last one is, for example, we have already shown you, right? If you don't zero pad, you have circular convolution problem. We must zero pad so that we can multiply the x and the h in the frequency domain correctly. Okay, I think with that, I will not discuss spectral leakage. You can read about it. And then actually we are done. Okay, so I think in this 40 minutes, 50 minutes, I have explained this O4C slides, part of it anyway. And you can now revise this.